Hi guys, this is A2 Chemistry, Analytical Chemistry, and we are doing Proton or H1 NMR. Question 1. There are four structural isomers with the molecular formula C5H10O that are aldehydes. Draw the structure of these aldehydes. So the functional group of aldehydes is CHO. So we draw a CHO for each of these isomers, which would always be the first carbon atom. And then, in order to make four structural isomers of aldehyde, we start with a straight chain aldehyde, which would be CHO, followed by a CH2, another CH2, another CH2, and a CH3, completing a chain of five carbon atoms and having the molecular formula of C5H10O. So this is our first aldehyde. In the second one, we make a straight chain of four carbon atoms and we substitute one of the CH2 groups on a carbon atom in which it will replace the hydrogen. So that carbon atom would become CH rather than CH2, and that hydrogen will add on to the CH2 group removed from the chain to form a substituted CH3 group. So this would be CHO, CH2, then we have a CH and a CH3. This is a four carbon chain, and the CH2 removed and the hydrogen removed together form another CH3 substituted group. So this is the first substituted aldehyde other than the straight chain. Now we can change the position of the CH3 group from being on the third carbon atom, counting from the CHO carbon, to being on the second carbon. So we can have CHO, then we have CH with the CH3 attached to it. Then we can have a CH2 and a CH3. So this is the third structural isomer with the molecular formula C5H10O. And in the fourth one, now that we have used both the positions for substitutions for a second CH3 group, we can have two substitutions on that same group. That means CHO bonded to a carbon atom only, because we will have two substitutions here, and a CH3 at the end, and two CH3s, one above and one below the carbon atom, producing the fourth structural isomer having the molecular formula C5H10O. Next, the NMR spectrum of one of these isomers contains four absorptions. So absorptions here is what is referred to as peaks. So the number of chemical environments present. So which isomer P, Q, R, or S gives this spectrum? So an isomer with four peaks, that means four environments present. So in the first one, we have the first environment as CHO. Then we've got a CH2 present between a CHO and CH2. This is the second environment. Then we have a CH2 present between two other CH2s. This is a third environment. We have a CH2 present between a CH2 and a CH3, making this the fourth environment. And then we have a CH3 present next to a CH2, giving us a fifth environment in this compound. So in altogether, we will have five absorptions in compound P. Moving on to compound Q. So we would have one environment with the CHO group. We would have a second environment with the CH2 between a CH and CHO. We would have a third environment with the CH present between two CH3s and a CH2. So this will be a third chemical environment. And looking at the CH3 groups present, both of them are attached to a CH. So both of them are present in the same environment. So both of them will give us the fourth environment for this compound. So altogether four peaks, and that is exactly what has been asked. So which isomer PQRS gives this spectrum? This spectrum is given by isomer Q, because Q will have four different environments present. Therefore, it will have four absorptions or four peaks. Next, predict the number of absorptions that would be given by each of the other three isomers. Okay, so we've already found out that isomer P gives us five absorptions. Now, to look at isomers Q and no, Q is also done, R and S. So in isomer R, we have an environment for a CHO group. we have an environment for the CH group, we have an environment for CH3 attached to the CH group, we have an environment for the CH2 group attached to a CH3 on one side and a CH group on the other, and we have another CH3 group. But this CH3 group is attached to a CH2, whereas the CH3 group, which was our third environment, was attached to CH. So this CH3 group is different. So this will give us a fifth absorption in the compound R. So R will also have five absorptions. Now to look at compound S, we have an environment for CHO. This will be our first environment. We will not have any environment for the carbon attached to CHO because it does not have any hydrogen present on it. Whereas if we look at the three CH3 groups present, this CH3 is attached to a carbon atom. This CH3 group is also attached to a carbon atom, and this CH3 group is also attached to a carbon atom. So all of these three will have the same environment present. So they will be the same group. So this will only have two absorptions present. So compound S has only two absorptions because of presence of two different chemical environments. Question 2. Compound K is a tertiary amine. It has three peaks in its proton NMR spectrum. One of the peaks is a doublet. Circle the protons responsible for the doublet. So if a peak is a doublet, it means that it has only a single proton or a single hydrogen atom in its adjacent environment. So if we look at the CH3 groups attached to nitrogen, they will be a singlet because they are attached to a nitrogen atom which does not have any hydrogen on it. The CH next to nitrogen would be a multiplet because there are two CH3 groups attached next to it. However, the two CH3 groups are attached to the same carbon atom which has a single proton on it. So accordingly, because there is a single hydrogen atom present in the adjacent environment, the peak for both the CH3 groups would be a doublet. So we need to circle the protons responsible for the doublet. So that would be this CH3 group along with this CH3 group because they're both having the same environment. So they will both have the same doublet peak. Question 3. The NMR spectrum of cysteine shows 5 absorptions. After shaking a solution of cysteine with a few drops of D2O, the NMR spectrum shows only 2 absorptions, E and F, shown below. So, when we add D2O, the peaks having labile protons would disappear. So, that would mean the NH2 peak would disappear, the SH peak would disappear, and the CWH peak would disappear. This would leave only the CH attached to the CH2 group as the environments giving us the two absorptions. So if we have a CH next to a CH2 group, that means that CH will have a peak split of 3 or a triplet. So that means E is the peak for the CH group, and the CH2 group being attached next to CH will have a doublet. So the doublet peak is for CH2. So the question asks, identify the two types of protons responsible for the absorptions E and F. So E is the peak for CH next to CH2, and the peak F is for CH2 next to the CH group. State and explain the splitting patterns of the absorptions E and F. So splitting pattern for E is a triplet due to the presence of two protons in the adjacent chemical environment And for F, we would state that it is a doublet due to the presence of a single proton in the adjacent chemical environment. Question 4. An unknown compound Z is propane-1-ol, propanol, or propanoic acid. The proton NMR spectrum of Z dissolved in CdCl3 is shown. From the proton NMR spectrum, identify Z. So, in order to identify Z, if we look at the functional groups, so the peak for the alcohol group ROH lies in the chemical shift range of 0.5 to 6.0 ppm, and this would be a singlet peak. So, we cannot see any peak in this region. So, it is not the alcohol. Then for the aldehyde, it would be RCHO peak, which would lie in the chemical shift range of 9.3 to 10.5. And in that range, we cannot see a singlet either, so it is not the aldehyde. And for the carboxylic acid, RCOOH, we would have a singlet peak in the range of 9 to 13, which is there. As you can see, it is very close to 12 ppm. So this is the carboxylic acid. Therefore, from the proton NMR spectrum, identify Z. Z is propanoic acid. And the peaks, this peak, the one near 12 is for COOH, and the peaks in the beginning, the one with the triplet is due to the presence of a CH2 next to it, and the quartet peak is due to a CH3 next to it. So the first peak is for the CH3 group next to a CH2 group, and the second peak is for a CH2 group next to a CH3 group, and then we've got the COOH. So all three environments of propanoic acid have been accounted for. Next, state one feature that would be seen and why in the proton NMR spectrum of each of the two compounds that are not Z. So for propane 1 all, there would be 4 absorptions present, because if you look at the structure of propane-1-ol, it is CH3 next to CH2 next to CH2 next to OH. So we've got 1, 2, 3, and 4 environments present in propane-1-ol. So there would be 4 absorptions present, a singlet in the range of delta equals 0.5 to 6.0 ppm would be present. And this singlet is due to the OH group, which is not there in the given NMR spectrum. So the next one is for propanol. So propanol would have a singlet peak in the chemical shift range of 9.3 to 10.5 for the CHO group, which is also not present in the given NMR spectrum. Question 5. NMR is very useful at examining hydrogen atoms in compounds. Explain why NMR spectroscopy can detect hydrogen atoms in molecules. So the reason we can actually detect hydrogen atoms using NMR spectroscopy is because of the ability of the nuclei of hydrogen atoms to undergo spin. So due to the property of nuclear spin, the NMR spectrum below was obtained from an organic liquid P which contains 5 carbon atoms per molecule. Okay, so we've got 3 environments. The first environment is be below 1 ppm, and it has got 9 hydrogen atoms in a single environment, and it is a singlet peak. That means either it is present next to the functional group or it is present next to a carbon atom without any hydrogen on it. The next peak is at around 2 ppm, and it is a singlet again with 1 hydrogen atom in that environment. And the third peak lies between 3 and 3.5 with 2 hydrogen atoms in the environment, and it is also a singlet. So, how many protons are present in one molecule of P, and explain your answer? So, we count the number written on the peak. So, 9 plus 1 plus 2 gives us a number of proton of 12, or 12 protons present. And explanation would be 9 plus 1 plus 2 equals 12. And that is how we obtained that there are 12 protons present in the given compound. When a little D2O is added to P, the absorption at 2.0 disappears. Okay. Explain what this tells you about the group responsible for this absorption and why. So this group contains a labile proton which undergoes proton exchange. So that is the reason why the peak disappears. And in order to explain what happens, we can write an equation. So ROH, the reason alcohol has been selected is because the peak at 2.0 has only one proton present, and it's a labile proton, and it has to be the OH group. So ROH plus D2O will give us RO, the proton replaced by a deuterium atom. So ROD plus HOD. So in this way, the peak for the OH group would disappear as it undergoes proton exchange and is replaced by a deuterium atom, which does not get detected in the H1 NMR spectroscopy. What does the absorption at 0.9 tell you about the adjacent carbon atom? So since it is a singlet, it tells us that the adjacent carbon atom does not have any protons present bonded to it. So since there are no protons on the adjacent carbon atom, we will have a singlet for the peak at 0.9 ppm. Next, what group is our responsible absorption at 0.9? Now, since 0.9 has a singlet peak with a 9 written on it, so this must be 3 CH3 groups present on the same environment. And finally, suggest a structure for P. So since we've concluded that there are 3 CH3 groups attached to the same carbon atom, so their peak would be a singlet. So now we are left with an OH group, which will be a singlet, and we are left with a CH2 group, which will also be a singlet because it is present between an OH group and a carbon atom without any hydrogen on it. Question 6. The NMR spectrum of Y given below shows 4 absorptions. Okay. What compound is responsible for the absorption at 0? So it will always be the compound TMS, which is a short form for tetra methyl silane, and that will be the compound always having a peak at delta equals 0. Compound Y is an ester with the molecular formula C4H8O2. Complete the table for the NMR spectrum of Y. The actual chemical shift for the 3 absorptions in Y and the splitting pattern for the resonance at 3.7 have been given for you. Use of the data sheet or data booklet may be helpful. Okay, so the peak at 1.0 splits into 3. That means it is next to a CH2 group, which means it is next to an alkyl group. And since this is an organic compound, this has to be a CH3 next to an alkyl group. So the number of protons in this environment would be 3 because CH3 has 3 hydrogen attached to it. And the splitting pattern as shown in the NMR spectrum is a triplet. Next, 2.3. So the peak at 2.3 splits into 4. So since it splits into 4, it is next to the CH3 group. So if it is next to CH3 group, it has to be a CH2 group. So on one side, a CH3 is present, and on the other side, because the chemical shift range is between 2 and 3, this is due to an alkyl group being present next to a C double bond O group or a carbonyl group or a carboxyl group, whichever it is. So if an alkyl group is present next to a C double bond O group, it will have a chemical shift range of 2.2 to 3.0, where we can see the quartet peak. Therefore, number of protons present in CH2 would be 2, and the splitting pattern as stated just now is quartet. QUARTET, quartet. So this is our second peak due to our ester. Now the third one at 3.7. Now this is a singlet peak. A singlet peak would mean that it is next to an electronegative group because the functional group in ester would be C double bond O and single bond O. And since we have got a CH2 and a CH3 groups attached to the C double bond O group, we are left with a CH3 group attached to the oxygen atom on the other side of the ester group. So the peak at 3.7 would be a CH3 attached to an oxygen atom having 3 protons on it and giving us a singlet splitting pattern. Use your conclusions to suggest a structure for ester Y. We've already identified the structure for ester Y. So this would be a CH3 attached next to a CH2, which is bonded to a C double bond O, which is bonded to an oxygen atom of the ester group, and we are left with a CH3 group attached to the oxygen atom. So the name of this ester would be methyl propanoate.